Hello and welcome. In this video, we are going to look at how to calculate total current in a parallel circuit. And so this circuit gives us an opportunity to look at parallel circuits in several different conditions. So in this first one, it says use when the switch A is closed. And so we're going to evaluate the circuit from the voltage source. That's going to be our perspective for the circuit. That's the direction our current is running. And so we'll look at the voltage source. It says that the positive leads on top, so we know that our current is leading out from that voltage source towards our resistance. From there, we can follow the current around, and we see that the first thing it hits is a node. That means parallel, right? Something is in parallel. So we can evaluate that node and see that as we follow down, we hit R1, and after R1, we go directly to ground. So R1 is in full parallel with something else in the circuit, any other pathway that we can make fully to ground at. And so as we continue on here, we'll see that we can continue through the node and go up towards A, which is closed right now. Switch A is closed, allowing us to flow through. We see switch B and C are not closed, so there is no connection to ground. So these resistors don't actually exist in this current flow. So we're going to ignore them. So we're going to follow A all the way down, and we see that it runs into R4 before it goes to ground down here as well. And so that means that R1 and R4 are in parallel with each other. And so when we write that out, we can say that our RT equation is equal to our R1 in parallel with R2. In this case, that's the R4 resistor here. It's the second resistor in the series. So at this point, we can evaluate that, but we are actually looking for the total current, right? So when we look at Ohm's law says voltage, current, resistance. If we want to know the total current in the circuit, and we'll do voltage over resistance. So we want IT equals voltage divided by resistance. And if we're looking for total, we need total voltage and total resistance. And so that is what we are going to shoot for, which means that we need to evaluate our total resistance equation here. So let's do that. On our calculator, we know that this is going to be that 1 over 1 over equation. There's a couple of ways we can do this. We only have two resistors here, right? So we can use our 1 over R1 plus 1 over R2. And this equation here tells us that voltage stays the same in parallel. That's all this equation says, right? Because 1, if we imagine this 1 is actually a voltage instead of a 1, and this one over here is also a voltage instead of a 1, then we got voltage over resistance, and we know voltage over resistance is current, right? So that means that we have the current down the first branch, R1's current, plus the current down the second branch, R2's current. Right? So we're just evaluating the two current loads, and we know that if we were to sum those together, KCL tells us that that would be IT. Right? If we add our two currents down the branches that we know are active, that's going to be all the current in the circuit, and those two summed together are equal to IT. And so that means that we have IT on bottom, right? And on top we have another V. Right, we have a 1 up here, and we said that the last ones down here represented the voltage. And so we're going to say that this also represents a voltage here. And so that allows us to say that we have voltage over IT, right? The source voltage divided by the total current. And that is Ohm's law for resistance, right? RT is equal to voltage over that. So that's why we use this equation. This equation is really nice. You also have a couple of other equations that can be a little bit easier to use. But remember, this one uses KCL. Right. So we're going to evaluate using this one. The other ones multiply on top and add on bottom. So you'll take R1, multiply it by R2, and then divide it by R1 and add it to R2. So watch out for this one. Make sure you do the parentheses on the bottom. This one's really nice when you get into rectangular and polar forms and AC waveforms. And so that can be helpful because of how we have to add and subtract rectangular and polar forms. And there is one more short trick if your resistors match. And so we'll skip that one, but we're going to stick with this blue one here, this one that discusses how voltage is the same in parallel. And that is what we expect from our parallel circuits, right? We expect voltage to stay the same. And so that means that at our node way back over here, when R1 split, the voltage that went down towards R1 was 9 volts, our voltage source. Right? And the voltage that went up towards switch A was also 9 volts. They both got the same thing, which means voltage stays the same in parallel. So we're going to use this total resistance equation here to solve for our total current, because we know that that voltage will remain the same, and we can just put a 9 volts up here for our total voltage of our IT equation. Let's do that. So we'll plug into our calculator here, and we'll say that we have 1 over R1, which we know is 2000. Look at the R1 and the R4 here, and we see that the R1 is 2000, and when we go over to that R4, it's 3.4 kiloohms, right? It's also 3,400. So we can leave them in kiloohms. We can say 2 plus 1 over 3.4, and we'll know that our answer is in kiloohms. We expect this answer to be less than the smallest resistor. So if you get this answer out and it's not less than the smallest resistor, evaluate it again. Look back again and make sure you've got all your decimals in there. Make sure you've got them all in the right spots. So now we know our RT. We can plug that in. We can say now RT is equal to our 1.259 kiloohms. Right? Everything else was in kiloohms. We answered in kiloohms. We didn't account for them, so now we account for them. Now we have our voltage total also, because that was given to us, right? That's our 9 volts total. So we'll put 9 volts on top. And we'll just evaluate this for our total current. Let's send this out. And we'll say that we have 9 divided by 1.259. Right? That gives us a kiloamps value. So we got to make sure that we multiply this by times 10 to the positive 3 so that we actually get our correct current out. That's a much smaller number. So make sure you account for all your zeros. You could even put it in as 1,259, and that would account for the zeros as well. That would move that decimal point back. Okay, so now we have our IT. IT is equal to 0.0071, we'll round that up, 5. And we'll move our decimal point back so that we get it into our notation here by 3 here. Then we have IT is equal to 7.15. That's our -3 location, so we'll put it at milliamps. And that is the total current for that piece there. So we're going to evaluate one more switch and see what happens with the next one. This is switch B. So switch B closes, and we end up opening switch A. And so when we look at the pathway for our current to flow, we see our voltage has not changed. It still allows our total current, IT, to travel up here. As soon as IT hits this node, it splits off into 2 different branches, I1 and I2, right? And that's going to go down branch B this time instead of branch A. Right? So branch A is open and branch C is open. So we're going to not use either of those 2 resistors. And we're going to just use the R3 resistor, the 820. So let's find our goal here. Our goal is to find total current down this new branch, and so our IT is the goal. We know that's Ohm's law, so we can bring that out. Our voltage source divided by our total resistance, RT. Remember, if we're going for total, we need to use both of our totals, and we know that V1 is our voltage source. It's also the voltage total. And so we can solve for our RT next. We haven't found that yet. We'll say RT is equal to, and we'll evaluate that using our calculator over here. Send these ones out, even clear these ones out. And this one, we'll do our 1 over 1 over equation. And we'll say that we have 2000, so 2K right there. We know that that's in thousands, right? But we look at the other one, R3, and that's 820. So what if we made that one into thousands? Right? Let's move 820 into thousands. So if we have 820 ohms and we want to make it kiloohms, we need to bring it from our base location and move it forward by 3 and put our decimal point there. So now we have 0.82, that 0 doesn't matter anymore, kiloohms. Right? So we'll leave our 3 at 0.82 k ohms. And that's how we can evaluate that. So back over here, we'll say that it's 1 over 2000 plus 1 over 0.82. That's the same as 820. And that gives us kiloohms out, right? That means that we have 0.581. We'll round that up for that 5 kiloohms. We can make that into ohms since that's not a very nice number, right? We can evaluate this further and say that we actually have, if we move our decimal point back here, 1, 2, 3 locations again, we end up with 582 ohms. Right? Okay, so now we can use that to determine our total current. So we'll send that out and we'll plug into our current equation. Voltage source was still 9 volts. That didn't change, but our pathway changed. So that's going to change how our current is going to be in this circuit. So we'll divide that by 582. And that gives us a larger current. Right? We have less resistance in the circuit, so therefore we have more current than the previous circuit had, than the switch A had. So 0.0155. We'll move that decimal point over 1, 2, 3 locations. And we'll get a total current of 15.5 milliamps. Right, and we got one more after this, right? So switch C. We move down to switch C. We should see that this is a similar kind of concept here. We'll clear out our calculator again. So here we have our 9-volt source, battery still in the same spot. We can trace that up and see that our IT splits again to I1 and a new I2 current down branch C. Right, these other ones are open, therefore there is nothing in those circuits at all, not even a potential voltage or current, so we'll cross those off because those resistors don't exist in this circuit. And so now as we trace down through here, we go across switch C down through R2, which means that that is our I2 branch. So we can go after our IT again. We say that IT is equal to our voltage source divided by our RT, and we are going to evaluate RT first. So our RT is the parallel combination of our 2K and our 1.1K. And so now let's try a different one. Last time we did the other two, right? So in this one, we can say that the 2000 multiplied by the 1100. And if we put a parenthesis here, it'll allow me to divide that entire thing by the addition of those two. 2000 plus 1100. Right? And that gives me the 720 or 709. And that is the other total resistance equation that you can use. The textbook does show both. And sometimes one is easier than the other. This one only works if you have 2 resistors. 709.6, so we can even round that up to 710. And that is in ohms because we brought everything down, so we could just leave our ohmic value there. We know that this value had to be smaller than R2. Right? R2 was 1.1K. R1 was bigger than that, so we know that this, whatever this value calculated out to, it had to be less than the smallest resistor. Okay, so now we can plug back into our IT equation. We'll send this out and say that voltage source, 9, divided by our total resistance, 710, going to give us a current value here that's kind of in between the last two, right? Our IT for this one is 0.012. We'll round that up to a 7. We'll move our decimal point over. So that's 1, 2, 3 back. So that's our -3 again. And we'll set this equal to 12.7 milliamps. All right, that's all we wanted. Let me know if you guys have any questions.